that we can get a protocol. You got to make a protocol, then you can go for testing for carb. We will go for carb testing, okay? We're mindful of it. We will be doing that. I just wanted to turn that over to Mike then. I'm sorry, I wanted to answer that question for people. And as far as what happens when it freezes, you'll find that out in the class.
This class, we are going to cover things ad nauseum. I'm going to make you sick with science. I'm going to make you incredibly dizzy with the mechanics of what goes on inside of an engine, because perhaps I haven't properly conveyed it before. I want you to understand what you're trying to accomplish. And to understand what you're trying to accomplish, you have to know what you're dealing with, what you're up against, what's going on inside this thing, what's going on with the HAFC components, how are they working together, how can you tune it to get the mileage. I mean, we've had several vehicles. One that comes to mind is a 99 Pontiac Grand Am. Went through the class tuned it. I think it got like 33 miles per gallon baseline. Took it back out after the class was done. The mileage came back like 48. It was just under the 50%. And so, gentleman that you're going to meet tomorrow, and I, Jimmy, went out and we just tuned it a little bit, played with it some, and then sent it back out, and it went from 48 to about 68, just by tuning. Okay, that's the make it or break it, is the tuning. Now, in order to tune, you have to understand what you're trying to accomplish. I've heard back from many technicians, I turn the knob, but it doesn't seem to make a difference. I don't know what it is that I'm trying to look for because, it's just not working for me. So if you understand what you're trying to accomplish and you understand where to look to get data from your scan gauge, if you know what you're looking for and what you're trying to get it to do for you, then hopefully we can take this dozen out of 80 and turn it into 90% success rates. Now, I'm going to put some responsibility on your shoulders. What I'm going to cover here is assuming that you have a working knowledge of an automobile, the auto cycle engine. We're going to get into tuning, and I'd like to recommend a few books to you. If you're not comfortable with what I'm talking about, this is like a 101 course book. It's called Electronic Fuel Injection. It's by Ben Strader. It is not the best book I've ever read on the subject of tuning, but it'll introduce to you basic concepts. So if you're coming from ground zero and you know how the carbureted vehicles work. You've tuned distributors with weights and springs, but this modern fuel injection stuff, you're not on top of. This will give you a crash course. It's a very inexpensive book. I don't see a price on it here. But this is one that will help you. A much, much, much better, more in-depth book is How to Tune and Modify Engine Management Systems by Jeff Hartman. I love this book. So here's two sources that will introduce you to the concept of tuning. Both of these books are designed to help you take an Excel DFI, a link, a mega squirt, a standalone system, sit down with the laptop, and create the whole operating parameters for the fuel and spark management system on an engine. And if you can do that, this is a cakewalk. These books are for when you replace the factory computer with an aftermarket computer.
For the chip. Okay.
That's what these books are written around.
So you cannot do with the original.
How to Tune and Modify Engine Management Systems by Jeff Hartman. Yes, I will pass these around. That's a good idea. If you want to get ISBN numbers or anything like that, these are my personal books evidenced by the coffee stains. So I would like them back. And then another one, although seemingly somewhat off subject, is Maximum Boost by Corky Bell. It's on turbocharging. The reason that it's pertinent to what we're doing is because when you take a naturally aspirated vehicle and you add a turbocharger, you got to do something with the fuel and the spark, because the turbo is going to add way more air than the engine and the computer was designed to see, and so you got to add more fuel. Furthermore, when you're adding more pressure in the cylinder, you got to start retarding the timing, because the flame will propagate a lot faster when you have a whole lot more air and fuel molecules in that same cylinder space. You got to retard the timing. So although maximum boost does get into how to physically mount the hardware, it also gets into the tuning side of turbocharging. So these are 3 very good books that I would like to recommend, because the problem that we are having is in the tuning. And the last book, what qualifies me to teach this class? I wrote the book on fuel economy, the ultimate fuel economy book. This I wrote. Gets into a lot of different things. That one's actually a 10-year-old version. I got it revamped, and then the computer crashed, and I lost all the pictures. So I don't have the new version uploaded on Cafe Press yet. But that book can be purchased at www.cafepress.com/FET. I'll write that in small print here. Nah, you're not going to be able to read that. Just remind me, and I'll write it down after we cover this other stuff. So anyways, our objectives are, first and foremost, it's listed number 1. Why? Because it's the most important. Make money. That's what you're here to learn to do. Make more money than you are making currently. There's an opportunity here, a phenomenal opportunity for you to be making anywhere from $50 an hour to $250 an hour for your time. Of course, now I know all of you are making at least $1,000 an hour, so this is kind of a pittance, right? No? This actually sounds good? Great. Because the HAFC is sellable. How many know people who would pay a lot of money to get double the mileage, even 50% better mileage? Pretty much anybody that owns a car, right?
Sure.
Yeah. So do we have a marketable product?
Very much.
All we have to do is package it, sell it, and then properly install it. Now, Dennis is your man when it comes to the marketing side of things. That's what he does. That's who he is. He's Mr. Marketer. So if you do 3 or 4 installs and you're not getting results, that's probably going to be the last 3 or 4 you do in your community, because word's going to spread, right? But if you do 3 or 4 and your lousiest one gets you a 55% increase and your top dog one gets you, 120, 130% increase, word's going to spread. And when word spreads, people are going to come knocking on your door. You don't have to go out and solicit. Word of mouth, man, the best salesman that you could ever have. People come to you. So we need to make money with this. This is infrastructure building. And if I send you out of this class, you don't know what you're doing, you go out and you flop on 3 or 4, when we need help with the bigger stuff, the PICC, you're not going to be around. You're not going to be interested. But if you're making money with the HAFC, when we're ready to slam the PICC on the world, you guys are there and you're saying, bring it on, baby, bring it on. So we need to get you making money now. We're going to learn about the PICC. You learned a little bit with the presentations this morning. I'm going to get a lot more in depth on the science behind that. This is going to be a science class, so don't do a lot of math, but we are going to talk very rudimentary science principles, because that's what's going to make all this make sense for you. We're going to learn how to properly install the HAFC. Now, in your manuals, everybody who's in the class get a manual. My manual shows page 5. These objectives are listed. There's only 4 in there, and I have 6 on the board. The 2 additional ones are learn how to tune the HAFC, and then learn to teach the program. Tuning is key. The hardware is worthless without the tuning. And then in the back of the manual, there's some additional fuel economy tricks that we're going to cover. Because let's say you get that one bugger, you've done 7 installs, you've had great success, you're averaging 60, 80% or better, and then this one vehicle comes in and just, for the life of you, you can't, 43% is the best you got. Time to cheat. Back of the manual, additional fuel economy tricks. Now we can bump it up there because we're guaranteeing a 50% increase. You guys are the ones that are responsible for fulfilling that guarantee. So if you got to cheat, by all means, cheat. So, any questions on these objectives? Silence is consent? Okay. Okay, the Ultimate Fuel Economy book that's being passed around can be purchased at www.cafepress.com/FET, which is short for Fuel Economy Tips. Okay, everybody knows how an engine works, right? You draw air into the engine, you spritz a little fuel in there, the piston comes up, the spark plug goes off, it explodes, and bodies fly, and the piston goes down, right? Sort of. Combustion efficiency makes more power and improves fuel economy. The better you can make the combustion efficiency, the better the results, power and economy-wise. Combustion efficiency can be denoted on a dyno as brake-specific fuel consumption, BSFC for short. Let me know when everybody has this. Anybody not have this? Yeah, CAFEPRESS, cafepress.com/FET. Yeah, it's not case sensitive. Combustion efficiency. What we're going to do, we're going to take chemical energy in the fuel. And first, we're going to convert that to thermal energy. By burning the fuel. When the fuel burns, it creates heat. That heat expands the nitrogen, water vapor, carbon dioxide, and other gases in the cylinder, pushes down on the piston, creating kinetic energy. Combustion efficiency is converting the chemical energy to thermal energy and then kinetic energy. So how well can we do that? That's our combustion efficiency. That's on page 9 of my manual. And I know some of these manuals are a little bit different. When the spark plug fires, we start an ignition. Everybody knows that. But there's something that happens before that. When the piston's coming up on the compression stroke, you're building pressure. You're building thermal energy. An air compressor, when you take this much air and make this much space out of it, you're taking the same thermal energy and compressing it also. The result is, if you put your hand on the outlet pipe of an air compressor, it leaves a permanent mark. It's so hot.
That's where you cool them down. That's where you have fan.
Turbochargers have after coolers or intercoolers, because compressing the air takes the same amount of thermal energy in this much space and condenses it into this much space, and we note that as a raise in temperature. So as the piston comes up, we're going to increase pressure, we're going to increase temperature, and now that starts to destabilize the fuel and the oxygen. We're going to take a hydrocarbon molecule, gasoline molecule, and the first thing that happens is, let me draw something out here. This is very simplistic, very, very simplistic. This is a propane molecule, and I'm going to get back to this a little bit. Propane is a 3-carbon hydrocarbon molecule. We're going to introduce oxygen gas into this, okay? Oxygen gas, when things start happening, the oxygen is going to go and rip one of these hydrogens off of this propane molecule. All right? This is called an OH radical. It's a radical because we have a little empty arm here that wants to grab onto something. It's ionized. It's charged electrically. This is the building block of combustion, the OH radical, because the oxygen is very stable in its O2 gaseous form. The pressure and the temperature will start to get the hydrogen wanting to attract here and start forming water. The first step is an OH radical. Then it'll go and it'll rip off a second hydrogen and make a stable water molecule. Meanwhile, now we still got carbons and so forth, so then another oxygen will come along. And it will snag onto one of those carbons. So now we have a CO, carbon monoxide radical. And then another oxygen comes along, and it'll eat up this free hydrogen here and turn into those magnificent OH radicals for us again. Everything goes through an OH radical in the combustion process. When we look at the formulas, hydrocarbon fuel plus oxygen yields carbon dioxide, water vapor, and thermal energy, heat. It's all done one little micro step at a time with an OH radical. That process doesn't happen without thousands, if not millions, if not trillions of these OH radicals, chiseling away, eating away at those hydrocarbons. In the meantime, sometimes you'll just get a break, just like that, where these will fly apart. It's a thermal catalytic cracking process. All right? Why is this important to understand when you're talking fuel cell technology? What are you trying to accomplish? All right? I'm going to go back. I know there's probably questions on this. I'm going to touch one other thing and then ask if there's questions. How many scientists in here? Who can tell me on a periodical table of elements the atomic number of oxygen?
8.
Thank you. So that means we have in the nucleus 1, 2, 3, 4, 5, 6, 7, 8 neutrons. 1, 2, 3, 4, 5, 6, 7, 8 protons, right? All right. And then we're going to have an outer valence here. How many electrons do we have in that first outer valence? 2. We have 2 electrons in that first outer valence. So those 2 electrons are negatively charged. They're going to offset 2 of those 8 protons in the nucleus. So now the second one, we're going to have, I think it's 4. Maybe it's 6. Yeah, I think it's 6. At any rate, we have a little hole here and a little hole here. That would be state, no, it is 4, because that's right, because we have 2. All right, I'm sorry, guys. I studied up on this so I could teach it. You know what? 1, 2, 3, 4, 5, 6. We have 6 electrons, and we have 8 protons, which means that oxygen has a double negative charge to it.
What are you describing? What
I'm describing an atom
atom
of oxygen.
of oxygen? Okay.
Macro and micro are the same. So if you want to see the big picture of an atom, look at our solar system. Okay, we have the sun in the middle. We have planets that are all orbiting around that keep everything balanced. Take one of the planets away and watch our whole stinking solar system just fly out into space. So we got to keep it balanced. So this oxygen has 2 more protons than electrons. Let's take a look at hydrogen. Hydrogen has 1 proton and 1 neutron, and it also has an outer valence. So to balance this, we would need 1 electron. Now, assuming that we're going to put this into a molecule, that electron may not be there. Hydrogen has a net positive charge. So we got 1 positive charge here. We got 2 negative charges here. No, that is right. Oxygen has not 6, but actually 2, 3, 4, 5, 6, 7, 8, 9, 10. Thank you. I knew there was, So we have 2 more electrons floating around. Then we have protons in the middle. Oxygen has a double negative charge. I'm remembering it as I go. So here we have hydrogen that has a net positive charge. So what we wind up doing is we take the hydrogen and we're going to kind of bump it up here.
what will be the magnetic forces? They will try to combine, or they?
Magnetism.
Yeah, they will try to.
Yeah, they want to stabilize them.
Okay.
So here we have a hydrogen atom sharing one of those little electrons with the oxygen atom. And then we throw another one out here. This is how it mathematically, electrically balances to create a stable water molecule.
And this is like liquid water.
Liquid water, water vapor, ice. Those are three forms of matter. Plasma is a fourth, and I'm going to get into that here in just a moment. So we have two hydrogens and an oxygen. This is getting down. Now we can go into quirks and stuff. I'm having trouble with this, so you know I'm going to screw that up. When we write this, I would write like this. This is the oxygen, and it has the two electrons that want to grab onto something. And we're just going to plug those little arms with hydrogens. So now we've gone from the very scientific formulation to my little abbreviated version here. Are there any questions on this? Okay. So everybody got this? This is not on the test, by the way. This is over and above stuff that I've never covered in any class before, and I'm hoping to, raise that 12 out of 80 some to, 70 some out of 80 some, or maybe 80 some out of 80 some success ratios. Four states of matter known to man at this time. Solid, liquid, vapor, and plasma. Solid. Let's use water as an example because everybody's familiar with that, the most plentiful substance on the face of the earth. Solid would be H2O, ice. Liquid would be H2O, water. Vapor would be H2O, humidity. So this morning when we got up, we had a little bit of this on the windshield of the vehicle. This is what Dennis was drinking earlier. Humidity is what's in the air. We can't see it, feel it, taste it, smell it, but we know it's there. In the summertime when he has these panels going, I can point and say, see the liquid water at the top, and then you can see it's turning to ice, and where did it come from? The air. Makes a nice little illustration, but it's a little too cold for that one. Plasma is H plus H plus O. In other words, when I drew out that water molecule before, I had to combine the two hydrogens with the oxygen to make a molecule. That's the way it looks here, here, and here. But when we get into plasma, now we have a free-floating, double negative charge oxygen. We have two free-floating, positively charged hydrogens that aren't connected to anything. Okay? Does everybody understand the four states of matter?
Yes.
All right. We're going to talk a little bit about the PICC here. At atmospheric pressure, water will convert to plasma at 3,800 degrees Fahrenheit. Now, I do not know what that is in Celsius. I apologize. But follow along. You'll get the gist of it if you're not familiar with Fahrenheit. At atmosphere 3,800 degrees, you put it under a perfect vacuum, and now it only takes 720 degrees.
Tilt the board just a little bit. I've got a light on, yeah.
So if we can put the water under a perfect vacuum, 30 inches of vacuum, we can turn it into plasma at a whole lot less thermal energy. Okay? Now, when we get into the fuel cell a little bit later, we're going to show how we take water and an electrolyte that will help the water conduct electricity. We're going to throw a voltage potential across it, electricity. And that voltage potential will dissolve the molecules into monatomic atoms. Basically the same thing, free-floating atoms. Because remember, Dennis said, we're not creating stable diatomic oxygen gas and hydrogen gas. We're creating monatomic hydrogen and oxygen molecules. Atoms. Brown's gas, water gas. So we're doing this at close to room temperature. We're not getting anywhere near these kind of temperatures, yet we're turning the water into a cold plasma. Because by definition, you have just free-floating atoms. Well, that's plasma. Except it's not even at 720 degrees. It's going to be like 180 degrees or something by the time this thing comes up to operating temperature. So let's see here. We're going to do the PICC, and we're going to have an exhaust pipe, and up through the middle of that exhaust pipe, we're going to run a fuel pipe. And up the middle of that fuel pipe, we're going to throw a ferrous reaction rod. The exhaust will be traveling in one direction. The fuel will be traveling in the opposite direction.
It doesn't matter if they both go in the same direction.
Yes, it does. They have to go in opposite directions. So you got a nice warm day. Cold front moves in. You get the hot and the cold air colliding and enfolding on itself, and just the frictional hot and cold starts building up a static electricity in the atmosphere. And that electricity builds and builds and builds, and finally the atmosphere can no longer contain all that energy. It's got to reach equilibrium, because that's how Mother Nature works. And all of a sudden, lightning bolt.
Million volts, millions of
Lightning bolt. Where did all that energy come from? It came from the hot and the cold colliding with each other. So here we have hot and cold going in opposite directions. We have a little mini thunderstorm going on in here. You can take a compass or a Gauss meter while one of these engines are running, and from about 4 feet away, that's about 1.33 meters, from 4 feet away, you can actually detect the magnetism on these things running. That's how that rod magnetizes itself, as Dennis told you. So now, like I said, we're going to cover the fuel cell in depth, and we know that electricity can split the atoms. We have hot exhaust coming down through here, not 3,800 degrees worth of hot exhaust, but we have some thermal energy. We're going to take and we're going to work towards that threshold that's necessary to turn our fuel into plasma. And then we're going to run hot and cold in opposite directions. We're going to build up a tremendous magnetic field with static electricity. I did one of these once where I put a little sight glass in the end of the fuel tube. So the fuel actually came in into a T, and I had a glass tube where I could look in there. In a room like this, you turn the lights out, it gets pretty dark, right? Because there's no windows. So in a room like this, I was running this generator And I'm looking down that fuel tube, and what I saw was this.
Why?
A blue aura. Just like if you see a spark plug firing, that blue electrical arc. I saw a blue aura around the rod, between the rod and the fuel pipe. There was that much static electricity that it created this nice little blue aura. Now we got electricity. I mean, we got electricity. That will help to lower the threshold necessary to convert our fuel into a plasma. Also, we talk about, atmospheric pressure versus vacuum. We're going to draw the fuel through under a vacuum. That's going to lower the threshold. I mean, it's going to make it easier to turn the fuel into a plasma. So, let's spell it out. We're going to use exhaust heat. We're going to pull the fuel through under a vacuum. We're going to generate an electromagnetic field. Electricity and magnetism are two separate phenomena, both incorporated into this. There's a fifth one. Don't tell me I know that. Ah, that's right. When the fuel comes in through that fuel pipe, before it hits the rod, it's moving along at a certain velocity. Now, it's got this much room to get through that pipe. When it hits the rod, it's going to accelerate because it no longer has this much room. Now it has this much room. So our objective is to accelerate that fuel to the speed of sound. Mach 1. Or better. Preferably Mach 1. Any airline pilots in here? Does anybody know what happens if you take an aircraft to the speed of sound?
It blows.
It blows apart. Why? Something about that harmonic frequency, it just tears everything apart, doesn't it? So the speed of sound will further destabilize our otherwise stable molecules to blow them apart. So we take fuel, diesel fuel, soda pop, A1 steak sauce, hot sauce, and we're going to run it up through here. Now, what is soda pop, right? I mean, it's water, hydrogen, oxygen. That's all good stuff as far as running an engine, right? And sugar. What's sugar? Hydrogen and carbon, right?
Everything's carbon on this, so I think just different forms of molecules.
Yeah, mostly just different forms of hydrogen and carbon with a few other things thrown in here and there. But mostly hydrogen and carbon. You blow it apart in a plasma field. Once you get past that plasma field, those conditions are no longer present. It's just like you take an ice cube out of the freezer. In the freezer, it's stable in a solid form. That water likes being a solid. And take it out, on a hot summer day, put it on the blacktop, it won't stay a solid very long, will it? It'll first convert to a liquid, and then it'll evaporate off, and an hour later, the whole ice cube's gone. So once we take our fuel outside of this plasma chamber, now you're going to want to start stabilizing those atoms into molecules again, right? But if we take a complex crystalline structure sugar molecule and blow it apart into a bunch of different atoms, Mother Nature's lazy. Mother Nature's not going to reconstruct that complex molecule at the other end of this thing. It's going to go into natural gas or propane or ethane or butane or just enough to stabilize it. And that's it. Well, geez, your engine can't run on sugar, but it can run on ethane and propane and natural gas and stuff, right? So do you get the concept of what's going on inside that little pipe in a scientific-minded way? Are we violating any natural laws?
Not yet.
Are we actually doing real black magic?
No.
No. We're combining simple everyday laws. There's not a scientist on the face of the earth that won't say heat will turn fuel into plasma. A vacuum will help that along. An electromagnetic field will do it on its own, but it certainly will help things along. And the speed of sound is known to destroy marvelous works. So does everybody understand how those little presentations could actually be doing what Dennis was showing you this morning? Make a lot more sense now?
Yes.
Great. Great. Any questions on it? Now's the time to ask because I'm getting ready to get off track. Yes, sir.
What's that little, the little valve you call that turns, that expands it? Like the expansion valve, what do you call that little tube that's inside? The rod. Yeah, the rod. What do you call that?
Reaction rod.
Okay.
That's just nomenclature. Yes, sir.
Are they doing anything to, I guess, increase the acceleration of the gas, through the line?
Okay, the question is, are they, I don't know who they are. Oh, me? Am I doing anything to accelerate through the fuel through the rod? Yeah, it's called pressure differential. All right? So if we have atmospheric pressure on the inlet side and we've got a high vacuum on the outlet side, that is going to, shall we say, suck the fuel through. Okay? So it's a pressure differential between the inlet side and the outlet side.
Are there some other mechanical things that you can do to
Basically also,
make that
it's
faster?
like a pump.
Venturi tubes or?
No, I mean, the reaction rod inside that fuel tube is the Venturi tube. It is the expansion valve. That's the magic. That's it. We don't need to assist that along any further other than just get the flow going and create a pressure differential between the inlet and the outlet. It happens.
And that pressure differential needs to be accurate, needs to be efficient so that it gets the right amount of pressure right through it. Am I right?
It's forgiving.
Is it?
Yeah, it doesn't have to be meticulously spot on, computerized,
that would
but
help.
there has to be a sufficient, and it's a threshold thing.
Right.
As long as you have minimum pressure differential, any more than that is good, but any less than that, it just doesn't work.
Right.
So making it, double that pressure differential doesn't double the efficiency. It's either working or it isn't.
That metal rod, the more fuel goes through, the more it magnetizes, the decrease the magnetism and the...
It's not because of the fuel going through, it's because of the hot exhaust gas going in one direction, the cold fuel going up the center in the other direction. It's that cross flow that generates that magnetic field.
But is it change the property of the magnetic field? Let's say in the beginning, when you put it first, when you start to run, it stays constant or increase its magnetic properties?
It will stabilize.
Stabilize at some
If
point,
I understand the gist of your question, you're saying if you take a plain steel rod
It's not magnetic.
and you take a compass and you go up and down that steel rod and you establish if there's any north or south biases on that rod, kind of mark it. Take that rod, put it into a PICC, run it for a while, pull it back out and recheck it. Yes, it changes.
And
Now, if you
constantly
take
keep
a-
changing or it stops at some
It will stabilize. So if you took a magnet, not just a piece of steel, but a fully magnetized rod, and using a Gauss meter, not only establish where the poles are, but the intensity of those poles. Put it into a PICC and run it long enough for it to stabilize, pull it back out. The plain steel rod and that permanent magnet will match. The magnetism from the permanent magnet will tone down to where the system wants it to be. The plain steel rod will generate a magnetic field,
it's gonna
and the
stop
two
at
will be the
some
same.
level, it'll be the same. Wow. Okay. Thank you.
Any other questions? Yes, sir.
The tube that goes through it, the alloy of that tube, does it matter? You got a ferrous rod.
Ferrous rod, ferrous fuel pipe. I'm still doing more experiments on the exhaust pipe.
Okay.
I have 2 reactors being made up for this van. One of them will be a 304 stainless, which does not conduct magnetism, but does conduct electricity. And the other one will just be a plain old aluminized pipe like all the rest of the pipes that you've seen here.
And basically the electric current you was looking around the rod, this is almost like cold fusion. I mean, this is also a reactor in a sense.
That's why we call it a reaction chamber. Yes, it is kind of sort of a
This
reaction.
alone solve the
As
basically
far
the-
as changing the structure of the atom, where cold fusion, or hot fusion for that matter, it actually takes one atom and changes it to a different atom. So you got your periodical table of elements. You're going to go from carbon and you're going to turn it into, say, helium and oxygen. I'm not making any promises we're doing this. There's evidence to support that, but I am not going on record by saying that it does happen. But I will be more than happy to say we're going to break down stable molecules, turn them into a plasma, let them recombine into something smaller.
But this solves basically energy problem also for electricity too. You don't.
Well, if you can use
And
crude
it's
oil
actually-
right out of the ground, how much energy is wasted in the refinery process? So if you can just take the crude oil and just dump it in the tank, you're not bellowing all that pollution in the air at the refinery. You're not consuming all that natural gas to power the refinery. Shoot, man, all that electricity that it takes. Skip it all, just crude oil right out of the ground.
Wow.
Any other questions? All right, I'm going to move on to the automotive application of this here now. Basic reactor. At the inlet side, that is the short version of the PICC system. Let's label some stuff here. We're going to inject fuel into an area upstream of the fuel pipe of the reaction chamber, just like you saw. They used glass jars or whatever, but we have to admit the fuel into the reactor. Now, Mother Nature has a few quirks about her. One of them is there's never absolutes. So that means we're going to put some fuel in here that's going to go through unscathed. It's going to go in as a dodecane molecule, come out as a dodecane molecule. So we're going to cool it back down then through a little radiator that is commonly called a condenser. All right? Anything that's going to turn back into a liquid will hopefully do it at this stage. If we missed anything through the process, which we will, because again, we're dealing with Mother Nature. She doesn't always cooperate the way we want her to, so we got to plan around her way of doing things. So then any liquid will go into the liquid vapor separator, LVS for short, liquid vapor separator, where it'll trap those liquids. Now, of course, this little reservoir here will have a float on it, and after it builds up so much liquid, it'll pump it back to the main tank to go another round. So what it comes out of here then is going to be in a nice vaporous state with maybe a light aerosol. And then we're going to take and go through a pump and into a holding tank. So from this point to this point, this is our high side. Think air conditioning systems. From this point back around this way to this point is our low side. Again, think air conditioning systems. Do we have a pressure differential between the inlet and the outlet? Is that pressure differential favorably biased so that we're putting essentially a net vacuum on our fuel pipe, pulling the fuel through?
Yep. It's like a pump.
Now, as far as a cold start goes, we're going to come off this tank here. We're going to go to a propane mixer. or propane carburetor as they're sometimes called. Now we can get this off the shelf. Someone else developed this. They have all the electronic controls to make this work.
Yep.
So we can deliver that fuel through a propane carburetor. That means that we can go, and there's companies all over the world. Practically every engine application you can imagine, there's propane delivery systems for. We can take our high side and run it through a little regulator. And we can bring the pressure in line with what the propane carburetor wants to see. We can have a little pressure switch on this tank. And after we build up so much fuel pressure, shut the pump off. Just run off what fuel you've already converted for a while. Pressure drops, pump kicks in, we start making fuel again. Electronic injector feeds the system, so when we shut the pump off, we also shut off the injector. Now there will be a hydrogen generator. And we're going to pump in the hydrogen through the same block that we're going to inject the fuel.
Combined in that block?
Yeah, the block's going to basically have an outlet that goes into the reactor. We're going to be taking the already reformed fuel, recycling it back through again and again and again and again. And each time we do, we break it down a little more, a little more, a little more. We're going to add hydrogen in here. I'm going to get into some chemistry, and it'll make 100% perfect sense why that is required. And then whatever liquid fuel that we actually put into the tank that's going to be converted, we inject through here. Hydrogen has to be pumped in because this is our high side. So we can't let it draw it in. It won't do that. It'll push back and, you know, kick us in the butt. So we actually have to have a small pump to pump the hydrogen in. Cold starts, propane carb fires it right up, just like you had, you know, propane or natural gas. Once you got the system primed, so initially you're going to have to start the car, you're going to have to run it, you're going to have to keep the propane carb turned off, and you're going to have to build up pressure. So as an installer, you would put the system on, hook up all the electronics, get all your plumbing run, and then fire it up and actually run both systems, but with the propane carb solenoid unplugged, so it doesn't actually run that in. So your gasoline engine will run its stock injectors, power the engine, generate the heat that we need. The alternator will generate the electricity to run our two pumps, and you build up fuel. As soon as that pressure switch says we're loaded, now you can reactivate the propane solenoid and never run the stock system again. I don't care if you're in Alaska. Cold start off of pre-made fuel. Is that beautiful or what?
Well, okay, on the Hondas, you don't have propane. I mean, you use the same thing with the regular gasoline.
We'll be using gasoline. We're even looking into the possibility of taking petrol engines, gasoline engines, and opening up the fuel tank restrictor, putting another sticker on the fuel filler door that says diesel fuel only. Because now the owner of that vehicle can go into their motor department of transportation, reclassify that vehicle as a diesel, emissions exempt. Who cares if it has a catalytic converter? Who cares if the EGR valve is working? It's now a diesel classification, and, you know, in all 50 states at this time, it's just a free pass.
It's a free pass, absolutely. Although they're considering catalytic converters on diesel too.
08s already have them. The 08 diesel.
It's not required. It's not Monday.
No,
it's
no,
just the-
well, okay, the OEMs, the Freightliners, you know, the Mercedes diesels have catalytic converters on them for 08. They require the low or the almost zero sulfur fuel. So if you're using the normal diesel fuel, you killed your catalytic converter like that. So are there any questions about this? This is a generic layout of the direction we're going with the production automotive version PICC. Nothing on, this is on the test. Yes, sir?
What's LVS again?
Liquid vapor separator. All it is it's something that'll catch the liquid and separate it from the vapors. So we can take the vapors and move on with them and then recycle the liquids back to our main tank.
It's almost like an accumulator.
an accumulator, right?
Is something specifically designed for that system, or you guys using something that's already designed like this?
There's a lot of variables that we don't know. One of the things is we're looking for a propane equipment manufacturer that's willing to work with us, who has the capacity to deliver the volume and the diversity that we need. You know, I mean, there's still a lot of things up in the air. I'm going to share a little interesting story with you guys. I'm working with a propane equipment manufacturer, retailer, that has opted to go through the EPA certification programs. And the first thing they have to do to certify their system is they have to take a stock vehicle that meets stock pollution standards. And the man told me that they take, you know, they certify a couple dozen vehicles a year. And they'll take brand spanking new, right off the rollback, you know, the delivery. It's never been titled. It has maybe 10 miles on it. They take it in, and it fails the certification stock before they do anything to it. They can get one with 10 or 15,000 miles on it that's broken in. So you're saying, well, you know, the engine's not broken in. No wonder. Okay, great, fine. I'll give it to you. How about one that's got 10 or 15,000 miles on it that's broke in?
Perfect.
Won't pass. Their biggest hurdle is they have to get the stock engine to pass emissions before they can move on to step 2 to certify their propane equipment. And he said they've never had one single vehicle pass. They've had to modify them all to get them to pass before they could even put their propane stuff on it to get it to pass. Now, the standards for a stock vehicle are here. When they do the propane conversions, you would think as long as they can meet these standards, they're good to go. Our EPA's up. You fill in the expletive. The standards for them to certify their propane system are way up here. First of all, the OEM's standards are here, and there ain't a vehicle out there that'll meet standard, according to this guy. And so the EPA challenges them. The EPA takes Dodge to court. Dodge shows up with 30 attorneys and a couple $1 million, and the EPA backs off, says, okay, well, you know what you're talking about. These little guys developing propane systems go in, and, well, Dodge said it passes. Nope, sorry. The EPA is very biased against alternative fuels. Now, let's say that 2001 Dodge van 5.2 Magnum V8 propane conversion was developed in, let's say, 2005. All right? They got around to it. They went in, spent the tens of thousands of dollars to get that van system certified. Okay, so if they did it in 2005, it's certified for 2005. January 1st, 2006, it's no longer certified. They got to do the whole freaking process all over again on the exact same system that was certified last year. The requirements didn't change. Their standards are still the same, but EPA has made it cost prohibitive for alternative fuel companies to maintain certification that way.
Who are those people? I mean,
This is just for your information. It has nothing to do with the class or the program, and we're doing a different route, but nevertheless, just wanted to share that with you. I thought it was mind-boggling. Okay, any questions on the PICC? Very good. Let's see here.
One question on the older vehicles, could you do a direct conversion where you don't have to pull?
There's propane, dual fuel propane carburetors for carbureted vehicles. They have a float ball on the side and they have a solenoid. Actually, 2 solenoids. One that opens up the propane passage and closes off your jets. And then you want to run it on the gasoline, it'll open up the jets and close off the propane. So that's why we want to go off-the-shelf stuff. I mean, if you're going to list every single vehicle combination out there possible, including diesels, oh, geez, man, there goes our 4 days just trying to say, yes, we can do those, yes, we can do those. But if we're doing just off-the-shelf components, there is a propane delivery system made for anything and everything on the road. If we can get our little PICC system working, if we can make the fuel, someone else has made the delivery stuff for us. Not only have they made the delivery stuff, it bolts right on. The clamps, the brackets, and so forth are kept to a minimum. We'll still have to do some fabrication as installers, but it's a minimum. Plus, you throw a wideband oxygen sensor in there, and these cats already worked up the feedback system. All we got to do is just go in there and program where we want it to cycle around. It's all done for us.
More or less, they fool them around. They just make them believe that what they read is accurate.
But it's all done for us. We don't have to engineer any of that. It's beautiful. Page 14 in my book. There is, it's listed as heating the fuel, but at the bottom of the page it lists out different hydrocarbon molecules. You'll see hexane listed. Hexane is hexagon, 6 carbons. Let's draw one of these buggers out once. So we've got 6 carbons. We're going to do this all straight chain, nothing fancy. 2, 3, 4, 5, 6 carbons. And then, of course, the carbons have 4 negative electrons wanting to grab onto something positive. Oh, like maybe a hydrogen. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you got 6, you double it, you know, and then add 2. C6H14, hexane. Hexane has a vapor point of 156 degrees Fahrenheit at atmospheric pressure. If you put it under a vacuum, what happens to that vapor point? So that means it takes less energy to vaporize hexane if you got it in an intake manifold at cruise, right? So we take this hexane, we draw it in through an injector into a low pressure intake manifold, and it's vaporizing incredibly fast because we got way more than 156 degrees in that intake manifold cylinder head combustion chamber as it is, and then we're going to put it under a vacuum, instant vapor. But then the intake valve closes and the piston starts coming up, and then what happens to our boiling point, our vapor point? It goes up because now all of a sudden we've got, you know, 150, 180 pounds of pressure in there. So that goes a whole lot higher. So we're doing a seesaw thing, huh? Remember the OH radical thing? Where we start putting oxygen in there and it just starts nibbling away at the hydrogen first and then the carbon second? Yeah. Now 156 degrees Fahrenheit, it's less than 1 millisecond to burn that. That OH radical process nibbling away takes less than 1 millionth of a second to happen with hexane. Now at the other end of the spectrum, we have dodecaine. Dodecaine